should be transparent for the material inside the spheres, and the object would swim if it would be allowed to exchange the material from one sphere to another. So in the first part of my talk, I will show you that once you replace water with a liquid crystal, then even a simple sphere, a single sphere, can swim in such an environment. So before I go to that, let me just remind those of you who are not familiar with liquid crystals, what the liquid crystals are. Some people know it very well. Bogdan, of course, wrote very nice papers on the subjects that I am discussing. For those who are not familiar, I will just explain that liquid crystal is a fluid that is comprised of anisometric molecules. In the ground state, the molecules would like to align parallel to each other, and we call this direction the director. It's a non-polar entity, but it gives the anisotropy of all properties of the liquid crystal. If you measure the, for example, dielectric permittivity or optical birefringence along the direct, or optical index of refraction along the director and perpendicularly to it, you will get different results. Because of this orientational order, liquid crystals also show some elastic response. If you would like to change the ground state in which the molecules are parallel to each other into a deformed state, like this picture shown here, then what happens is that you have to perform some work. And this work goes against the elastic response of the liquid crystal, which is the integral over the distorted volume of the gradients of the director field and some elastic constant. Now, there is also kind of surface anisotropy. Each boundary that is adjacent to the liquid crystal will try to include some orientation of the director. And in order to change this orientation, one again would need to perform some work. And obviously this work will be proportional to the area of the container and some coefficient that characterizes the interaction between the wall and the liquid crystal. So you have two energy terms. Clearly, if you integrate this elastic energy over the volume, you would get something that scales linearly with the size of the system. So the elastic energy will be L, and the surface energy will be quadratic in the size. So let's just apply this simple balance of two different scalings to the simple question. What would happen if you have a uniform liquid crystal cell and you place a droplet there? The droplet, just for example, wants to see the director being perpendicular to its surface. So how this frustration will be resolved? Clearly, if you compare the two energies and how they scale, you would realize that if R is very small, and that means smaller than K over W, then this inclusion is not going to distort the director because the elastic penalty will be very high. But the surface anchoring penalty will be very small. WR squared is small when R is small. Now, if you have a larger inclusion, larger than some ratio of these two energetical parameters, K over W, then the droplet should obey the surface anchoring conditions, and you would expect that the director will be distorted in the neighborhood of this colloidal particle and will try to be perpendicular to the surface as expected. So this is one of the potential configurations. But if you look at it, you would realize that there are too many distortions. The director kind of forms the entire Saturn ring of disclination. And as was shown by Lubensky and his colleagues, a little bit more energetically favorable situation is when this Saturn ring shrinks into a point at one of the poles of the droplet. Of course, the balance is very delicate, and you can prepare cells in which either this hedgehog structure or this Saturn ring structure are more stable. For example, if your container is shallow, then you can stabilize this Saturn ring. But if the container is infinite size, then this structure on the right-hand side will be energetically preferable. So the question is, what would happen if instead of just a droplet of water or a colloidal solid particle, you will have an active droplet? Active means that inside this droplet, there is a motion, let's say, of bacteria or maybe some artificial microswimmers or maybe some chemically powered colloids. What would happen with this situation? And the next slide shows you the movie, the experimental movie, with the answer. So what you see here a droplet of water that moves from left to right. The surrounding medium is a liquid crystal, and this kind of locus of brightness on the right-hand side is nothing else but the hyperbolic hedgehog, as we call it. This is the defect that I was talking about in the previous slide. So what you don't see is that inside this water droplet, there are many bacteria that chaotically move. And if you, for example, place a pure water droplet in the same condition, in the same liquid crystal, you would see no propulsion. The droplet will just experience normal Brownian motion. It will move left and right, up and down, but it would never propel in a deterministic fashion as shown in this movie. Here I just demonstrate how the horizontal axis changes with time. You see it's a linear function. There is practically no propulsion along the vertical axis. Okay, so I mentioned that the structure might be of this dipolar symmetry, or it might be also quadrupolar symmetry with the Saturn ring. And this movie is demonstrating that the symmetry of director distortions around the particle is of quintessential importance for the dynamics. So we prepared a shallow cell in which the ground state is more or less corresponding to the Saturn ring. But time to time, the fluctuations in the system produce a shrinkage of this Saturn ring. Here, it shrinks to the left, and you might see that the particle moves slightly to the left. And then in here, it moves to the right. And you can see that when it moves to the right, the Saturn ring is actually shrinking into the point on the right-hand side. I'll show you one. Yeah, right here, the disconnection ring shrunk into a point, and suddenly the sphere moves to the right. So this is just a graphic presentation of what you just saw in the movie. I show here the different states of this droplet. If it has equatorial Saturn ring, it does not move. The displacement as the function of time is practically zero. But if the Saturn ring shrinks here to the left, it moves to the left, then it comes back to the symmetric position. There is no displacement. And then it shrinks to the right, and you see immediately that the entire droplet shifts to the right and acquires the highest speed once the Saturn ring is shrunk into a point. Okay, so what is the role of the liquid crystal here? Let's just see what would happen if we slightly increase the temperature and the liquid crystal melts into the isotropic fluid. So you see when it's a liquid crystal, the director fluctuations produce this flickering. Once we heat it above 35 degrees centigrade, this is the running temperature. You see 30, 31, 32. So we heat the liquid crystal. Once it's isotropic, the propulsion stops. So this active droplet is not going to propel itself when the environment is isotropic. To get a little bit more insight into what's going on, let's consider what's happening with the fluid water inside the droplet. Here you see the interior of the droplet visualized with the help of these fluorescent particles that show some movement. You don't see the bacteria, but you see that the bacteria create chaotic motion of the fluorescent particles inside the droplet. And if you make the vector field of velocities inside the droplet, you would see that the bacteria create kind of chaotic flow. There is nothing that would be directed from right to left or top to bottom. It's really a sequence of vortices and chaotic changes. But then when you look outside the droplet, this is the exterior flow, you would and map the velocities of the fluid of the nematic liquid crystal outside of the droplet, you would see some well-defined directionality. You would see that there is a flow from right to left. And this is in this associated with the droplet. In the laboratory, somebody
Вас плохо слышно, извините.
Oleg, do you have problem with microphone?
Yeah, somebody is playing with the mic. So you see that the exterior rectifies the flow, and the flow that is chaotic inside becomes organized outside. So what is the mechanism? Here I show the director field around the inclusion. If the particle, because of the fluctuative flow inside, moves to the left, you might see that the director is distorted different from the original state. If it fluctuatively moves to the right, you might see that the director is also distorted differently from the neutral position. So in other words, if I have these fluctuative displacements of the sphere caused by the interior activity to the left and to the right, the effective director field and the associated viscosity of the medium would be different for the motion to the left and motion to the right. And because of that, we rectify the situation and we create the active force proportional to the difference in the effective viscosities of the surrounding and proportional to the average value of these bounces of bacteria inside the droplet. Of course, since the motion is force-free, this propulsive force is totally compensated by the viscous force, and you can calculate the velocity of the droplet that would be proportional to the difference in viscosities in the nematic liquid crystal. So with this, we can now play many games of controlling the dynamics. Here you see the nematic liquid crystal in which we pre-patterned the underlying director, so it's in the concentric geometry. And as you might see, all these little active droplets follow the circular trajectory. We can apply electric field and distort the liquid crystal around the droplets. This is what we do in liquid crystal displays, changing by electric field the orientation of the liquid crystal, and the droplet would obviously change the direction of motion. We can also use the electric field to control the speed, because we can unwind this point defect into the Saturn ring, and the Saturn ring is not mobile. It is neutral, it does not move. And finally, we can also make a kind of bus stops. We can force the droplet to go to some location like the center of the radial defect and stop there, because once it's in the center of this defect, there is no more dipolar symmetry and the droplet has to stop. So with this, I would like to conclude the first example that nematic environment offers a mechanism of symmetry breaking that allows even a single sphere to propel itself. And by using the properties of liquid crystals, such as response to the electric field, we can control the velocity and trajectory of the active droplets. So, and the next portion will be about controlling the micro swimmers at the individual level. So here I'm not talking about a droplet of water in which we have hundreds of bacteria. I am talking about bacteria directly dispersed in the liquid crystal. Obviously, it cannot be the liquid crystal that one uses in liquid crystal displays, such as in your computer screens. It has to be the environment that is non-toxic to the bacteria. And there are water-based liquid crystals, such as the one shown here. It's comprised of molecules that are organic dyes. It can be even DNA molecules dispersed in water, and they form elongated cylindrical aggregates. And it turns out that since it's water-based and since there are no surfactants, this environment is safe for bacteria and they can swim in it. And here you see the bacterium strongly enlarged, swimming in the nematic liquid crystal. Here you see many of them swimming in the uniformly aligned liquid crystal. And what you notice is that they move apparently parallel to the orientation of the cylindrical aggregates, but they move with the same probability to the left and to the right. So that means that you cannot extract any useful work out of this. But that is our goal. We want this motion to be directional. And so the question is, can we do something to make this motion directional, to rectify it? And our approach was based on creating director gradients, creating these different alignment patterns. So the first example is circular geometry. You might notice that the bacteria move again along the director, but clockwise and counterclockwise motion are approximately of the same probability. On the right, I show you the radial configuration, kind of orthogonal to the circular. And again, the bacteria follow the director and then gather in the center, but then they escape the center. And again, the motion is not polar. But once you have something in between, something shown here, which is of chiral symmetry, you observe a very spectacular change in this scenario. As you might see, all the bacteria in this pattern, they swim in one direction. This polarity is counterclockwise, and it's characteristic of all the bacteria. So how do we understand these things? I showed you the bacterium on one of the previous slides as an ellipse with two equal forces. So one force is propulsive, another force of exactly the same amplitude, because the swimming is force-free, is a drag force. So for a physicist, the swimming bacterium, despite all the complexity, can be represented by a very simple geometrical form. It's an ellipsoid with two forces, the so-called force dipole. These two forces are opposite in direction and equal in the absolute value. So now let's come back and see whether this simple picture would help us to understand why suddenly in this pattern there is a circular motion. If you consider two bacteria close enough to each other, each of those bacteria is aligned by the director field. But since the director field is distorted, in the close proximity of two bacteria, I cannot compensate the vertical component of these two forces. I compensate the horizontal because they are looking in opposite directions, but I cannot compensate the vertical because both bacteria are tilted the same way. Now, if you mentally place the similar two bacteria here, you would realize that this uncompensated force is directed to the left, and then here to the bottom, here to the right. And in essence, you would expect that this interaction of bacteria produces the circular force that drives their motion, as you saw in the movie. And in fact, this simple geometrical presentation can be repeated in analytical form. Here I show you how this interaction between bacteria looks like in the analytical form. You can find it in pioneering works of Ramaswamy and Simha, also in this work, more recent. So this force shown in red here is a combination of splay and bend. Alpha is some activity constant. So since I know the director field in the pattern, I can calculate this particular force, and it's nothing else but this red field that is directly coinciding with the graphic presentation here. Then I can balance it with the drag force and arrive at the equation for the velocity. You see in this equation, written in the cylindrical system of coordinates, the radial component of force is 0, but the azimuthal is not, and it describes the experiment reasonably well. So it looks like the key ingredient in this collective motion is the close proximity of the bacteria to each other. If there will be no close proximity, they would not produce this active force. And we decided to verify this and did a number of experiments in which the number of bacteria would increase from very low to very high. So here you see a movie, and then this is the kind of the integral of the movie, when there are just few bacteria and they swim in this vortex inside the center and then outside. There is no collective motion. Then if you increase the number of bacteria, you might notice the first loops. And then if you add even more bacteria, you suddenly start to observe the circular motion as expected. Here, just for completeness of the picture, I show you the director field that is kind of curling in the opposite way from the previous slide. So now the motion is clockwise rather than counterclockwise. And the physics is the same. So if the bacteria are far away from each other, they don't feel each other. Their interaction is absent. But when they are close to each other, these uncompensated components of the active force produce the global active force shown in red, and that's what drives the rotation. Now you can play with the tilt angle of the director with this spiral angle, and you find out interesting things that now you also have the radial force. This radial force is absent in the case of 45 degrees pattern, but if the pattern is more like star-like, then there is a force that pushes the bacteria to the center. If it's more like the target or circular pattern, then this radial force is directed outwards. And this is exactly what you see in the experiments. Here I show that if you have a star-like structure, the bacteria are pushed towards the center. But if you have more like open structure, then the bacteria form toroidal swirls that expand in space. And finally, the goal is not to just observe some rotation of bacteria. It might be, of course, of interest for some little machinery that uses rotations, but one of the important modes is to have linear motion of bacteria. And you see here the pattern that is forcing the bacteria to swim strictly left to right. I intentionally do not show you the director field from the start. I just wanted you to think what it might be. And now that you have the opportunity to think, I can show you this structure. So this is a kind of a nail wall that is created in the liquid crystal. And this pattern forces all the bacteria to swim in one direction. And since they do so, you can force them to do a useful work. Here you see the colloidal particle that is being transported by this jet of swimming bacteria. So it's a very deterministic motion from left to right, and this motion now can produce useful work. So I conclude that the very simple replacement of water with the liquid crystal as the environment for the dynamics of microorganisms brings a lot of benefits. You can enable new mechanisms of propulsion, as you saw with an active droplet that would simply steadily go in one direction, and that direction can be changed, can be designed, can be modified by the electric field or by other means. And you also saw that even at the level of individual micro swimmers dispersed in the liquid crystal, you can do a lot of things. You can control their trajectories, polarity of motion, and you can even force them to perform useful work. So I would like to finish this presentation with just a little ad that our graduate program, or aspirantura in Ukrainian, is always looking for good students who would like to join us for our research, and we have stipends available for that. So if you are interested, please either contact me or apply at our graduate program's website. Thank you very much for your attention.
Thank you very much for very interesting lecture. Okay, we have 5 minutes on the question and comments. Who would like to ask Professor Lavrentovych?
May I ask a question about